Today we're going to take a look at the first part of our aqueous solutions unit. We're going to start with some key vocabulary terms as we look at the different parts of a solution. The first word we want to look at is solute. This is the substance that's being dissolved. This is typically going to be a solid substance. In our case, it'll typically be an ionic compound. The solvent is simply the substance that's doing the dissolving. For our intents and purposes, this is typically going to be water, the universal solvent. In order for something to dissolve, the attraction that exists between the water molecules and the ions within the solute must be stronger than the initial attraction between the two ions. In the picture you see here, we are dissolving sodium chloride into water. If you look at the second box, you can see here that all of these positively charged hydrogen atoms in the water line up to surround the negatively charged chlorine ion. Similarly, in this box, we see the negatively charged oxygens align with the positively charged sodium. The attraction that these water molecules have on the individual ions is stronger than the initial ionic bond. Because of this, the water molecules are able to pull the ions apart, effectively dissolving them in water. Typically, ionic compounds are going to be soluble in water, mostly because these ionic compounds contain the two differently charged ions, your positive and your negative ion, which are attracted to the partial positive and partial negatives within the water molecule. There are some covalent compounds that can be soluble. They must be polar or they must contain a hydrogen bond. We'll get a little bit more into that when we get into intermolecular forces. But for right now, consider most covalent compounds to be insoluble. Looking at the list of ions or ionic compounds at the bottom, it asks us to figure out which one we would expect to be soluble. Something like silver nitrate, we would assume is soluble, given it's ionic, and it contains that nitrate ion. Calcium chloride is also an ionic compound. It's most likely going to dissolve in water. C6H12O6, that's sugar. That's going to be a covalent compound that is not soluble in water. CH3OH, that's methanol. Yet again, a covalent organic substance, also not very likely to dissolve in water. Our last one here, PbCl2, we have to be a little careful with. This is an ionic compound, but remember lead is one of our exceptions to our solubility rules. This is actually going to be insoluble due to that lead ion. Taking a look at electrolytes, this is something you've probably heard a lot of if you drink any kind of sports drink, Gatorade in particular. These are strong electrolytic solutions. And what that means is that it has some substance. In the case of Gatorade, it actually has sodium chloride that completely dissolves in water. When that happens, it produces free ions. So consider, as you can see in the picture below, if I take sodium chloride and I throw it in water, I end up with Na+1 and the chloride ion, which is a Cl-1. These two positively and negatively charged ions are now able to carry an electric charge. In order for electricity to conduct, there must be charged particles that can carry electrons. So we have to see this movement of electrons from one to another. The more ions that will dissolve in solution, the more conductive the solution is. So these strong electrolytes are going to produce a lot of conducted electricity. If you look at the question here below, BaCl2 is going to produce 1 barium ion and 2 chlorine ions. My Ca3N2 is going to produce 3 calcium ions and 2 nitrogen ions. And then my sodium chloride, as we saw above, is going to produce a sodium and a chlorine ion. In terms of which of these would be the most conductive, it's going to be our calcium nitride. Because it has 5 total ions in solution, it has more opportunity for the movement of electrons, and we will therefore see a greater conductivity. Our barium chloride here would be our second most conductive, given that it has 3 total ions. And then lastly, sodium chloride would be the least conductive of the 3, given that it only produces 2 ions when dissolved in solution. In contrast, a weak electrolyte will incompletely dissolve in water. This does not mean it is insoluble. It simply means that it is less soluble than a strong electrolyte. Sugar would be a good example of an incomplete or weak electrolyte. It will partially dissolve, especially if you were to increase the temperature of the water or stir the solution. Think about making iced tea. When you pour sugar into your iced tea, simply stirring the glass will increase the amount of sugar that dissolves. Because it does somewhat dissolve in water, it will produce a small amount of oppositely charged ions, which then can carry electric charge and thus conduct electricity. These tend to be weak conductors. As you can see in the picture below, this first light bulb here is going to be my strong electrolyte. It's got a bright, bright light. It's got lots of ions in solution, so we see high conductivity. This is going to be a weak electrolyte, given that it has only a few ions that form when put into solution. The last one here is what's called a non-electrolyte. A non-electrolyte simply means that no dissolving occurs and therefore no electricity can be conducted. Again, a non-electrolyte, as you see here, is simply a substance that does not dissolve in water. Because there is no dissolution, just to clarify, we're going to use the words dissolve, dissolution, but you might also see the word dissociation. Dissociation is just a fancy science word for dissolving. So when we refer to something as dissociating, we simply mean it to be coming apart. Because there are no ions in solution, we see no conductivity. These are going to typically be your nonpolar covalent compounds. So think of something like carbon dioxide or any type of like methane, CH4. These are going to be nonpolar and therefore they do not dissolve in water and will not conduct electricity. Throwing it back to honors chemistry here, we're going to talk a little bit about molarity, which we define as the amount of substance that is dissolved in a given volume of solvent. We call this the concentration. The way I think of it, think of like Kool-Aid. If I make Kool-Aid the right way, it tastes the way it's supposed to. If I add too much water and I make it less concentrated, it's going to be watered down. Whereas if I don't add enough water, it's going to taste extra sugary. We measure in science here with a unit called molarity. Molarity, as you can see, is defined as the moles per liter of solution. So we start here with 15.43 grams of barium nitrate, and we add it to a beaker that contains 123 milliliters of water. The question asks then, what is the concentration or the molarity of the solution? First thing we need to do is convert those grams of barium nitrate over to moles. In order to do that, we need the molar mass. Remembering the molar mass we get from going to our periodic tables, and we're going to look up the individual masses of all elements involved in the compound. We then multiply them by their subscripts. So we're going to take the mass of barium and we're going to multiply it by 1 because there is 1 barium atom. We're going to take the mass of nitrogen and we're going to multiply it by 2 because this little subscript on the outside of my parentheses tells me there's 2 nitrogen atoms. We're going to take the mass of oxygen and multiply it by 6. Again, distributing my 2 to everything inside the parentheses. Adding them all up, I get 261.37 grams of barium nitrate per mole. You'll note we put 1 mole on top, so that the grams of barium nitrate would cancel out. In doing so, if we multiply across the top and then divide by the bottom, we find that we have 0.0594 moles of barium nitrate. Adding this to the liters of solution, note we've moved our decimal 3 places to the left in order to convert to liters. Dividing our moles by our liters, we get our molarity, 0.48 molar. This capital M here represents molarity. So just note when you see that large capital M, we're looking at the moles per liter of solution. If we want to make a solution less concentrated, we would dilute it with water. To figure out how much of the concentrated solution you would need to produce the correct volume of the desired concentration, we use the dilution formula. M1V1 equals M2V2. In this formula, M1 is the more concentrated solution. V1 is the amount of that solution. So what that should say to you is whatever volume you're plugging into V1, it should be describing the molarity that you've plugged into M1. M2 is always the less concentrated solution, and V2 is the desired amount of that solution. Again, as long as the volume describes the molarity that is on the same side, this will always work out. All right, let's take a look at an example. What volume of 16 molar sulfuric acid solution would you need to produce 250 milliliters of a 1 molar sulfuric acid solution? Given that 16 molar is the higher concentration, this is going to be M1. The problem does not provide a volume that describes that 16 molar solution. Hence, we are looking for V1. We are asked to produce 250 milliliters, which we will convert to liters. So we will move that decimal 3 places to the left. We want to produce 0.25 liters of a 1 molar sulfuric acid solution. 1 molar will be our M2, as it is the less concentrated of the two solutions. As you can see here, we've plugged in the 16 molar for M1, the 1 molar for M2, and the 0.25 liters for V2. Plugging into the equation, M1 times V1 equals M2 times V2. We simply multiply the right side of the equation and divide by 16, getting V1 by itself, finding that you would need 0.156 liters of this 16 molar solution. The AP Chem exam likes to ask lab-based questions. What this means is they're going to give you information and ask you to either write a procedure, write an error analysis, or analyze data that they provide to you. One of the common questions is asking how to prepare a solution given appropriate glassware. For example, in the problem we saw before, we started with a 16 molar solution and we wanted to dilute it down to a 1 molar solution. In order to prepare this in a laboratory setting, we first would need to calculate the volume of our 16 molar solution needed. We did this on the last slide. Then, once you know the volume of that 16 molar sulfuric acid solution, we would measure it out. So we would, using a graduated cylinder, Measure the needed volume. Because this is AP chemistry, we want everything to be as accurate as possible. So instead of simply dumping it into a beaker and adding some water, we're going to place the 16 molar solution in a volumetric flask. A volumetric flask is a very, very accurate piece of equipment. The way it works is it is a pre-designated volume. You simply add whatever it is you're trying to mix or dilute, and then you fill to the marked line. If you fill it to the marked line, it ensures with high precision that you have the exact volume listed on the volumetric flask. So our last step here would be to fill flask to mark. In this example, they would have given you a list of laboratory equipment. It most likely would have included things like graduated cylinder, beaker, volumetric flask, electronic scale, and what you would need to figure out is which pieces of equipment are necessary to complete this procedure, and then provide them with a step-by-step procedure in order to complete the task. Let's take a look at an AP practice problem. Let's say that an LPHS student prepares a 125 milliliter of a 0.1 molar sodium iodide solution. To this solution, the student adds 0.15 grams of lead 2 nitrate. The reaction proceeds until one reactant is completely consumed. Before we can do anything, we need to consider what is the balanced chemical equation that's taking place here. So we know we have sodium iodide. Looking at our sodium ion and our iodine ion, crossing my charges, I have NaI that is reacting with this lead 2 nitrate. My Roman numeral 2 indicates I have a +2 charge on my lead ion. Nitrate is an NO3 minus 1. Crossing my charges, I get PbNO32. This is a single replacement reaction, meaning my sodium ion is going to react to form a new compound that will include sodium and nitrate. I will have sodium nitrate, and my lead ion will react with the iodine ion to form lead 2 iodide. Again, my lead 2 has a +2 charge. My iodine has a -1. Crossing, I get PbI2. Quickly balancing. 2 iodines are on the right. I need a coefficient of 2 on the left. That gives me 2 sodiums on the left, and I need 2 on the right. That will give me 2 nitrate ions on the right and 2 on the left. One lead atom on both sides means we have a balanced equation. To answer the first question, calculate the grams of sodium iodide needed to create the solution. Well, let's think about what we have. We have a volume and we have a molarity or concentration. Recall, molarity equals moles over liters. When we have molarity, we have liters, we can find moles. So let's plug in what we know. I have a 0.1 molar solution. I do not know the moles, but I do know that I have 0.125 liters of solution. Simply cross multiplying my 0.1 times 0.125, I find that I have 0.0125 moles of sodium iodide. I want to convert this to grams. So I'm going to use the molar mass of sodium iodide. Looking it up on the periodic table, the molar mass of sodium is 22.99. I'm going to add to that the mass of iodine, which is 126.9. I get 149.89 grams for every 1 mole of sodium iodide. You'll note my moles cancel here. Multiplying across the top, I should find that I have 1.87 grams of sodium iodide. I want to know how many moles of each reactant there were. Well, I know how many moles of sodium iodide there were because I just solved that in the problem above. By taking my volume times my molarity, I was able to calculate that there were 0.0125 moles. In terms of moles of lead nitrate, I am given the mass of lead nitrate. I can go ahead and convert simply using my molar mass of lead nitrate. Starting over here, I have 0.15 grams of PbNO32. Setting this up, I'm going to put 1 mole on top. My molar mass here, I'm going to have 207 for my mass of lead, plus 2 nitrates, so 14 times 2, plus 6 oxygens, 16 times 6. I have a molar mass of 331 grams. Note, grams will cancel here. I'm multiplying across the top and dividing by the bottom. I find that I have 0.00045 moles of PbNO3. My third question here asks everyone's favorite, what is the limiting reaction? We want to know what limits this reaction. Well, take a look at your balanced equation. We have a 2-to-1 ratio here. What that means is whatever amount of lead nitrate I have, I need to have twice as much sodium iodide. So let's take a look. If I take the amount of lead nitrate that I have in this current problem and I double it, what do I get? Should get something like 0.0009 moles. Do you have 0.0009 moles of sodium iodide available? You do. Check this out. You have 0.0125 moles of sodium iodide available, and therefore sodium iodide is not the limiting reactant. You have more of it than you need. Therefore, our lead nitrate is our limiting reactant. We will run out of it long before we ever run out of sodium iodide. All right, let's take a look at one more. We want to know what the balanced equation for this reaction is. Well, we saw that on the last slide. So we know what the balanced overall equation is. If we take a look back, we can see that we had sodium iodide plus lead nitrate produced sodium nitrate and lead iodide. We simply balanced, and we had a balanced equation. We want to know the molarity of the NO3 ion after the reaction is complete. Well, we know how much NO3 there was to begin with, or at least we know how much PbNO3 there was to begin with. We know that it was the limiting reactant, so let's go ahead and convert moles of lead nitrate to moles of sodium nitrate. If we look, we have 2 moles of sodium nitrate, there's our ratio, for every 1 mole That tells me that there's 0.0009 moles of sodium nitrate. And I know that there is 1 nitrate ion for every 1 sodium nitrate compound. Therefore, if I have 0.009 moles of sodium nitrate, I have also 0.0009 moles of the nitrate ion. This question here asks me for the molarity, so I need to make sure that I take my moles and I divide them by my volume. So in this problem, my moles are 0.0009. We were told in the beginning of the problem that we had a 125 milliliter solution, which is the same as saying a 0.125 liter solution. So doing some math, what we should find is our nitrate ion has a concentration of 0.007 molar. In the last question here, it asks you to identify which of the following pictures accurately describes the system after the reaction is complete. Well, let's think. Look at your products. Something should stand out to you. PbI2, insoluble. This is a solid substance. So that tells me off the bat, this cannot be the right answer. There is no solid precipitate formed. It also tells me that this cannot be correct, as the solid precipitate is not lead nitrate. You also told me that PbNO3 was the limiting reactant. Therefore, I should not see any Pb ions anywhere in solution. So let's go ahead and cross out Aaron here. I'm left with 2 things up here then. I knew off the bat that I should have sodium and nitrate ions in solution, and I do in both of these last beakers. Remember, sodium iodide is in excess. That tells me that there's excess sodium and excess iodine. You needed to have a beaker that contains iodine ions. Mike P is the only one that contains the solid precipitate, the sodium and nitrate ions from the soluble product, and the excess iodine ions that are left over from our sodium iodide.